With turbulent flow problems and the minor loss problems, okay, there's three types of problems. Okay, the first type, you're given generally the diameter of the pipe, okay, and you're also given, and from that you can work out the Reynolds number and the friction factor, okay, and you just plug in the numbers in that you've got from the question into the equation to determine the pressure loss, okay. Now sometimes you'll just be asked to find the pressure drop due to friction, okay. Sometimes you'll be asked just to find the pressure drop due to minor losses, okay. Sometimes you'll be asked to find the pressure drop due to both, okay. Sometimes you may have to plug this number into Bernoulli's equation because there'll be an elevation change as well, okay, or there'll be a pressure difference between the two reservoirs, say, for example, okay. And so you need to make sure you answer the question. If there is an elevation change, therefore you must use Bernoulli's equation. You can't just use this equation because this doesn't take into account any change in elevation, okay. So you need to, this is the loss term, okay, and you just apply that equation. Type 2 problems. Guys at the back, okay, if you want to talk, then you can leave, okay? If you'd rather stay here, then shut up, okay? And that, obviously that applies to everybody else that's chatting as well, okay? Right, type 2 problems, okay? You're often given, this is a bit more challenging, you're given the pressure drop, okay, so you know what delta PL is, and you're given the diameter. But the problem is that you'll be needing to find flow rate, okay? And to get the flow rate, you need to know what the velocity of the pipe is, the velocity of the flow in the pipe. Now, although you've got diameter, we don't know what C is. We're not given C or V dot, okay? You've got to find it. And because we don't know what C is, we can't determine the Reynolds number. Reynolds number requires you to know the flow velocity, okay? So how can you find the friction factor? Well, you can't. But you can make a stab at it, okay? And so on the Moody chart, you have a guess. You assume full turbulence. Now, if you remember on the Moody chart, I go back to the visualizer. On the Moody chart, there's our Moody chart. Anything, okay, to the right-hand side of that dotted line, okay, we're dealing with full turbulence. And you'll know that these lines here, okay, which are associated with the relative roughness, the dark lines, they're horizontal. And so it doesn't matter whether we pick a point over here or pick a point over here. The friction factor is going to be the same, okay? And so the Reynolds number we can neglect. It doesn't matter. We know the relative roughness because we've got the diameter and we know the material of the pipe generally. Okay, so you just pick off the value. So I choose this one here. It doesn't matter where I choose it. I'm going to get the same friction factor of this value here, okay? Doesn't matter where I choose it. And so that's what you do with these problems. With the type 2 problem, you assume full turbulence. You make the assumption of full turbulence, so you don't need the Reynolds number. And then you get a value for F. You then go through and solve the problem, and you check your answer, okay? And so that may require some iteration. On the loop, the flow chart goes like this. We've got delta P and we've got D, okay? From that, you can calculate your relative roughness, epsilon upon D. Okay, you assume full turbulence to get your value for F. Okay, and then you go through the equation. Here's the equation here, the value to determine C. You plug in your pressure drop, which you've been given, density, which you'll know. There's your F value, okay? L upon D plus any minor losses that you've got in there, okay? And you go through the loop, solving for C, and you keep on going generally until C doesn't vary significantly, okay? Now, we're not going to give you lots of iterations to do, okay? Generally, you'll get a value that remains the same in the problem. The problem may even say, there's no need to iterate, or you can assume full turbulence, in which case you don't need to iterate at all, okay? And you keep on going round the loop until you've finished. Yes, is that a question?
I was just curious, when you word it significantly, is that like 0.1, 0.01?
Well, generally it'll be until your value of F is so close to what you initially determined that you can't really distinguish between the two, okay? That's what it means significantly. I mean, you'll keep going until you can't make any difference because of the resolution of the chart, okay? So that's the type 2 problem. Type 3 problem, okay? You're given the pressure drop and the flow rate, okay? And this is what's known as the pipe design problem because you've got to work out the diameter of the pipe. Now, not knowing the diameter of the pipe gives you a couple of problems because not only can we not work out the Reynolds number, but we also can't work out the relative roughness. Okay, so again, you need to make another assumption. And this time, we assume that we're somewhere in the middle of the Moody chart. Okay, so if I show you that, we're about in the middle, okay, somewhere around here. And so we just take this as our friction factor, as our initial guess. Okay, we assume F is 0.03, just an assumption. Okay, and then you go through and solve the problem. And if your values for D, if you get a value for D, then you can then work out a new Reynolds number and a relative roughness, and you can find a new value of F. And you keep going around the loop. Okay, and so the flow chart looks like this. We're given the pressure drop and the flow rate. You guess a friction factor. Okay, it's a complete guess. We choose 0.03. You can pick another number if you want to, but by guessing a value, you can at least then solve the equation using this equation. Okay. So you determine what D is. You then calculate a new Reynolds number and relative roughness, which will give you a new friction factor, and then you can calculate a new value for D. And again, you keep going around the loop until D doesn't vary significantly. Now with this equation, okay, this is the standard equation for pressure drop due to friction, okay? So this is neglecting minor losses, don't worry about that, okay? And what I've done is I've replaced C, okay? We know that V dot equals A times C. Well, if I plug in V dot over A into this equation, I end up getting this term, okay? And then I can solve there for D, which is the fifth root of the rest of that lot, okay? So you can see where that comes from. Because we've got D to the 5 down here. So that's a type 3 problem. So those are the problems that you'll have to deal with when you're dealing with turbulent flow and minor losses, okay? It'll either be you've got to find the pressure drop, okay, which you can then plug into Bernoulli's equation. You may have to find the flow rate, okay, in which case you need to determine the velocity of the flow in the pipe. Okay, and the last type is where you've got to work out the diameter of the pipe, okay? You'll be given, in any of those questions, you'll be given enough information to work it out, okay? But you may need to do an iteration to check your answer.